All right, so for this problem, I'm going to go over the next fluids problem from our worksheet. And so if you want, go ahead and stop it, but I'm just going to go kind of quickly through it because this one's, I think, a little bit easier than the others. And so the first thing it wants to know is the total time it takes to reach a maximum depth of 80 meters. And initially, it's going to accelerate at some rate until it reaches some constant velocity. And then it'll remain constant until it gets down to the total depth of 80 meters. And then it gives us the cross-sectional area of the bell of 9 meters squared, and then it gives us the density of seawater. Okay, so what I've written down so far is just the acceleration of 0.1 meters per second squared. I know that my final velocity is equal to 2 meters per second. And so the first thing I want to do is find how long it takes to accelerate this much, or I should say, how long does it take for it to reach this speed? How much distance has it covered in that amount of time? And then how much time does it take to cover that remaining distance? And so I can use the fact that VF is equal to V naught 0, plus AT. And so we have 0.1 times T here. And so you would solve for the time. The time then would just be equal to 20. So it takes 20 seconds for it to reach that. So T is equal to 20 seconds. And so how far has it traveled in that 20 seconds? Well, we would say delta X is equal to 1/2 AT squared. And so we'd plug in our acceleration of 0.1, our time of 20 seconds, and then we'd see how far it's gone in that amount of time. Now, however far it's gone, remember it has to go a total of 80 meters. So now you'd figure out how long does it take to cover that 80 meters going, or that difference, I should say, that difference in distance. How long does it take to cover that going at 2 meters per second? That's your other time, and then you would add it to that 20 seconds for your total time. So it's really similar to the last problem. All right, so let me bring up the problem here again one more time. The next part wants to know the weight of the water on top of the bell, and then the absolute pressure on the top of the bell at the maximum depth. And so the weight of the water, you could think of the weight of the water as all the water that's above that acorn. And if we're looking for the weight, we're looking for essentially what is the force due to that water on the acorn. Well, the force, what I'll say is that the weight, which is the force, is equal to mass times gravity. Our mass isn't given to us. That'd make it too easy, right? But we are given the area of the acorn, which is 9 meters squared, and we're given the height of the water, which is 80 meters. And so the mass, because keep in mind, the density is equal to the mass divided by the volume. And so the mass is equal to the density times the volume. And so that's density times the volume times G. And the volume, I can rewrite this again as is equal to the area times the height times G. And so plug in all your values. You have a density of 1,025 kilograms per cubic meter, an area of the shell, or of the bell, I should say, of 9 meters squared, a height of 80 meters, and G is 9.8, and that's equal to your total weight of the water. The next part wants to know what is the absolute pressure on that. Well, the absolute pressure is simply the atmospheric pressure plus the pressure of the water above you. And so my absolute pressure then, sometimes you'll see it written as P, but I'll write P absolute just to be clear. The absolute pressure is equal to the atmospheric pressure P naught, which is just 101,000 pascals, plus rho GH. Rho is the density of water again, G is the gravitational constant, and H is the height of the water. And so plug all that in, and that is your atmospheric pressure. The next part wants to know, so let me pull it up here so you can see. The next part wants to know the, okay, so we calculated the absolute. Okay, so the next part wants to know the minimum force necessary to lift open the hatch of the bell at the maximum depth, and then what could you do to reduce that force necessary to open the hatch? And so let me go back here. And so we're looking for the force necessary to open that hatch. Well, that force is, if you consider, when I first looked at this, I said, okay, well, it's the pressure that's on top of this hatch, which is the pressure, the absolute pressure I calculated earlier. But remember, the pressure, there is a certain pressure in the bell itself. There's a certain pressure because you wouldn't want you to have your bell that you're in to be at vacuum, because otherwise that'd be like you're in outer space, right? I mean, if you were to, I mean, you obviously couldn't breathe. There's no air in there, but you're because your body has some pressure associated with it too, due to the gases and stuff. All kinds of weird things would happen if your bell was at vacuum. And so the point is that the force that you need to calculate, you consider it the gauge pressure of the water above it. You don't consider the absolute pressure, and that's due to the fact that there's already some pressure in the bell. And so therefore, we would say that the force is equal to our pressure times our area, and our pressure is just rho GH times our area of that little hole. That little hole is a circular hole, which has a diameter of 0.25 meters, and so the area is pi r squared, so that's just pi times 0.25 squared. Now, if you consider that hole, you could say that there is some force due to the water above it pushing down, which is the reason it's so difficult to open. But there's also some force pushing up on it due to the atmospheric pressure of the air that's inside the bell, which is also pushing up. Now, the greater the difference in these two pressures are, the harder it is to open. And so if you were to increase the pressure on the inside of this bell, it would require less force to open, because you're sort of balancing out there. And so the greater the difference in pressure, the harder it is to open. And so therefore, if we increase the pressure inside the bell, it would decrease the amount of force that's required to open it. And that is all for that one.